I'm actually kind of curious why Zoom thinks it's like a good idea to have like this text to speech that tells people that the meeting's being recorded and have it at like full volume or something. Okay, let me plug in my whiteboard, then I'll tell you what we're doing for today. For those of you who didn't join in earlier, good morning. It's like 9 a.m. on a Thursday. Didn't rain this morning, so okay, so let me kill my touchpad. All right. So today I have like 3 things in store for you guys. I don't think it's like that much or that heavy, but we'll see. So one thing I'm going to do for you guys is I'm going to sort of like show you an application or like basically apply the decision tree lower bound like technique to show that like binary search is kind of optimal. So when I say like kind of optimal, I mean like if you're only using comparison-based algorithms, like if you're only using comparisons to implement like a search algorithm, then binary search is the best that you can do. Okay. The next thing that I'm going to do is I'm going to talk about like the full analysis for radix sort. So like a very general one, in case you didn't see that already. Okay, and the last thing I'm going to do is that I'm going to try to find a slightly better shortest path finding algorithm. All right, but like only very slightly. So you kind of like, I mean, there are like definitely much better algorithms out there, but I just want to sort of use this whole assumption on the input kind of technique to demonstrate, you know, like a better solution for shortest path finding. All right. So before I begin, are there any questions? I think like yesterday I was really busy, so I saw some questions, like some people sending me questions on Telegram. I'll get to them after this class. So like besides that, does anyone have any questions? Because if not, then I'll begin. Give you guys like a minute to think about single source faster path. No, shortest. That sounds funny. No questions? Okay, let's begin. Oh, forget that I'm on the same layer. Not eraser, pen. Okay, so let's talk about searching algorithms. And I'm pretty sure all of you should be familiar with binary search, right? And right now, like I want to ask, like the question that I want to pose to you guys is that if I was given an array of size n, right? So given array size n, right? Now, if I want to look for an item, right, in this array, and I want to only use comparisons, right? Like like one question could be why are we using binary search? You know, is there something faster in binary search? Can we do it in, let's say, like log n over log n time? You know, that sort of thing. Can we, like, this is faster than binary search, right? Because binary search is log n time. Like, or can we do it in maybe like square root of log n time, for example? Or like, could we possibly perhaps do it in, I don't know, something like maybe log n over let's say square root of n times, something like that. I'm not sure, right? Like, you know, so I mean, okay, actually this is very small, so it's definitely not this, but yeah, so these are questions you might ask, you know, like why are we using binary search? Why could we do something faster, right? And the idea here to show is that like any algorithm that you come up with can't you know, like any algorithm that you come up with that has to correctly solve the search problem has to use at least log n comparisons. Okay, so in case you're not familiar with the technique, let me explain it to you guys. The way that we do this for comparison-based algorithms is we try to think of like the algorithm like A as this sort of like machine, well, you know, that sort of like interacts with the input. So let's say A here is my input, I here is my, A here is my algorithm, I here is my input, right? And it interacts with, the algorithm interacts with the input. So when I say interact with the input, I mean like, you know, it kind of like asks the input to like look at two parts of it and say like, hey, like, is like AI less than less than AJ, that sort of thing, right? And what the input does for you is that it says yes, no. Okay, so you can think of a comparison-based algorithm as like, us limiting what the algorithm can really do to the input. Okay, like maybe you can do swaps, that's fine, but you can't really do much else than that. So like in the case of like Merson and Quicksolve, for example, they're actually like, they do swaps, for example, and they do like indirection. So you do store values in arrays, but you never store it based on the value. You only make all these decisions based on the comparison. So what you should really be caring about is the fact that uh, whatever decisions the algorithm makes is really only based on the comparisons that it does. All right. So in this sense, like the intuition that you should have in your mind is that your view, like the algorithm's like understanding of the input really is just based on like all the comparisons that it makes. Okay. So one way of thinking about it is that if let's say my algorithm made t comparisons, okay, so you can think of it as it asking t questions. So like question 1, question 2, question 3, until question t. Right. And all these questions needn't be the same. So like, for example, if like question 1, like when I say question, I mean a comparison, right? So like if the comparison said yes or no, right, like it could change, like it could influence whatever questions you ask, like whatever comparisons you make next. That's completely fine. That's completely fine. All right. But the point is that if I gave you if I gave your algorithm the opportunity to make t comparisons, right, the intuition here is that the most they can differ, the most different behaviors it can give, right? Like the most different, or like, okay, I would say the most number of different behaviors it can give is 2 to the power of t. All right, because again, like if you want to like think about this intuitively, it's kind of like if your algorithm asks the same questions on the input, right, and it gets the same answers, it should be doing the same thing because it understands the same thing about the input. Okay, or you can think of it as like maybe your algorithm would say, okay, I'm going to ask like these t questions, and like for every different result of like answers that I get, I'm going to do a different thing, right? So if you ask t questions, right, you get at most 2 to the power of t different answers. And if you get at most 2 to the power of t different answers, that's like the most you can, that's like the most different sort of like outputs you can give, or like the most like different things that you can do. Does that kind of make sense? Like stop me if it doesn't, because this is really important. Give you guys like a second to think about whether you have a question. Okay, feels like you guys don't have a question, so I'm gonna move on. All right. So you should really just think of it as like the algorithm asking the input. Like, like maybe your friend's gonna ask you a question, like ask you 20 questions or something. Then if there's like, if you have like 2 to the power of 20 plus like if you have much more than 2 to the power of 20 like possible like answers, like he or she is not gonna be able to narrow it down within 20 questions. Right? The same thing is happening here. So what I'm trying to say is that if your input has many cases, right? Like if your input has many situations that your algorithm needs to handle, and your algorithm doesn't ask enough questions, right? Your algorithm will not be able to know what to do. That's the intuition here. Okay. So if you want to prove lower bounds, and what lower bounds means is that we want to show that algorithms need at least some amount of running time. This is one neat way to show it, because like this doesn't say anything about running time, right? It just says that, oh, I need to ask like I need to make a minimum amount of comparisons. Then the next part of the argument says that, hey, since you need to make at least t comparisons, that means that you need to run in at least t time, because you need to access the input in at least like t time, right? So then you would say, okay, so the algorithm needs to run in at least time t, right? So this is really the crux of the proof. It's sort of to say that like we're going to show that like any algorithm that runs too quickly, can't possibly make that many comparisons. And if it can't possibly make that many comparisons, it can't handle that many cases. If you can't handle that many cases, then it's screwed, right? So I mean, like it's gonna take it's gonna take me much more time to explain the proof idea than to just give the proof, right? Because like that was the proof idea. So the proof is kind of simply like in the case of like you know, like consider like any consider a search problem, right? Where you're given like sort of an array, like well, given array of n items. Okay, and we want our comparison based algorithm to be able to find like, you know, where our item is, right? Like for example, I give it the value, it will give me the index, that sort of thing, right? So there are at least like there are n possible locations in the array where item can be, right? The item here being the item that we're looking for, the one we're looking for. So if there are n possible locations, right, we need to make t comparisons so that 2 to the power of t is at least n, right? Because again, if we make t comparisons, we can handle 2 to the power of t different cases, right? If there are n possible locations, that's how many cases we need to handle, right? So we need this. This is important, right? So for 2 to the power of t, if we need for 2 to the power of t to be larger than n, that's the same as saying that we need log of 2 to the power of t to be larger than log of n. That is just the same as saying t needs to be larger than log of n. So the proof is really, really short and simple. Does this make sense? Like it took me much less time to explain the proof than to give the proof than to explain what I'm trying to do. Stop me if you have questions, because that's all I plan to say about this topic. Because if something doesn't make sense, you should ask now. You know, what's t again? T is the number of comparisons, right? Number of comparisons that your algorithm makes. Remember? Because like we were trying to say that if your algorithm makes t comparisons, so you can handle 2 to the power of t different cases, right? If I have n cases, I need 2 to the power of t to be larger than n, right? Does that make sense? Like this is like the number of comparisons that your algorithm makes. Okay, maybe I should say you all, but like any algo should make. So note here that when I'm trying to do this lower bound proof, right, I'm not saying like give me binary search, I'll show you it needs at least log n, you know, or like saying give me some special algorithm. That's not true. Like this proof works for any algorithm, right? Because the statement that we want to make is no matter what algorithm you give me, it needs to make at least log n comparisons to find the element. Radix search, I don't know what that is. So do you see my point? Like if we ever ask you to do a lower bound proof, right? Most likely it'll like in the context of 3230, what this means is that we will ask you, we'll say, okay, we need you to show that this is like, you know, like you need like any comparison algorithm needs at least this much time. In which case, right, your proof should never be something like consider binary search, or like, you know, consider like quicksort and then show that it needs at least this much time. Because then you're fixing a specific algorithm. That's not what we want. What we want to show is that if you give me any comparison-based algorithm, it's going to need at least that much time. All right. So it's a much more general statement. And the way to prove it is that you need to do this. And you realize that in this proof, right, I say nothing about the algorithm. Like I don't care how the algorithm does it. The algorithm could be like the smartest thing in the world. My point is that if it doesn't make that many comparisons, you can cheat it. Can you explain why it's 2t again? Okay, so it's like okay, if let's say I had so think of it this way. If I make t comparisons, right, how many possible combinations of answers can I get? They're all yes, no, right? So if like, for example, like maybe this is like let's just list it on the table. So there's comparison one. For example, if I make 3 comparisons, so comparison 1, comparison 2, comparison 3, right? That there is a possibility that it's all no. right? There's a possibility that it's like yes, no, no. There's a possibility that it's no, yes, no, right? Like how many possibilities do you have here? You have two, like if I make 3 comparisons, right? This is like 8 different possibilities of like results that I can get with my comparisons. Does that make sense? Like I don't know how my algorithm is doing the like I don't know what my algorithm chooses to compare. I just know that when it does these comparisons, right, there are like at most that many different possibilities, right? So if I have like if my algorithm makes 3 comparisons, that's 8 different cases. Like that's 8 different possibilities, right? It's like all no's to like yes no no to like no yes no to like yes yes no, that sort of thing, all the way down to like yes yes yes, right? So what we can do is we can just pretend that our algorithm sort of says like, okay, for every different case, it will do something different. Like for this case, maybe it'll like output something. And for this case, it'll output something. And for this case, it'll output something. For this case, it'll output something different. Yeah, it's like a binary tree. That's right. So you can think of it as like the thing is this: when you want to prove a lower bound, right? When you want to prove that something's impossible for algorithms, or you want to prove that algorithms need some minimum amount of time, right? The difficulty is that you want to say something like any algorithm you give me needs this much time, or like any algorithm you give me needs to do this much work. Okay, the difficulty with this kind of question is that we don't know what people can do with the algorithm. See, solving problems with algorithms are kind of easy to some extent because it's like all you have to do is come up with one solution. I mean, okay, I know it's not really always simple. There are definitely problems that are difficult where we don't really have an algorithm. But my point is that the opposite thing to do, right? The antithesis of like solving something algorithmically is to show that you can't, right? Or for example, to say, oh, under comparison-based sorting, we can't do, like we can't sort faster than like n log n, or like we can't search for items faster than log n. The issue is that when you say something like, oh, quicksort runs in n log n time, so I guess that's the best we can do. Or when you say, oh, binary search runs in log n time, so that's the best we can do. That's not really a proof, because it just sort of like shows that, or like whatever algorithm you could come up with is only that efficient, right? It doesn't say that there are no algorithms. It just says that I mean, like someone could tell you, yeah, you're just lacking imagination. Maybe there's like a really smart algorithm out there that no one knows, right? So this, when you try to do this proof, right, you have to sort of like accept the fact that you don't understand what the algorithm is doing, right? Like in this case, if you look at this proof, when I try to make this argument, right, I don't understand what the algorithm is doing. The algorithm can do whatever it wants. My point is that no matter how hard the algorithm tries, or no matter how intelligent the algorithm is, right, if it doesn't make enough comparisons, right, it can't handle enough cases. And if it can't handle enough cases, because like you should think of it as, if I make, like, for example, 3 comparisons, right, the algorithm can only do at most 8 different things, right? Because if it makes the same comparisons and it sees the same results, it should always see the same thing. It should always say the same thing, because the algorithm is only going to base its decisions off the comparisons, nothing else, right? It doesn't do it based on the values of the input. It only does it based on the comparisons, right? So this is a very strong assumption, but when you assume it, you get very nice things, right? So then because again, if you have, like, for example, 3 comparisons, it can only see at most 8 different outcomes from its comparison. So it can only do at most 8 different things. So this is the intuition that you should be having, right? It's the same as the binary tree idea. The binary tree is sort of like you trying to keep track of the internal state of the algorithm. Every time you make a comparison, you move down the binary tree a little bit, right? So you can think of that as like internally what the algorithm is trying to do. So each leaf on the binary tree is sort of like a different behavior of the algorithm, right? So if the height of the binary tree is at most t, right, you can have at most 2 to the power of t leaves. And each of those leaves like sort of denote like a different behavior of the algorithm, right? So if you have that, then you can use this to say, okay, if the problem I'm trying to solve has many different cases, right, then I'm going to need at least that many comparisons, right? So I hope the proof idea makes sense. So if you look at the assignment, there's like one question that I don't think needs to be submitted. The one on nearly sorting or whatever. That was actually the question I was gonna give you guys, because like it came up for my midterms when I was taking CS3230 and I wanted to like show it to you guys. But I think it's good if you guys like try it yourselves. So the idea behind solving those kind of problems is that you want to do two things. I mean, you want to do one thing, right? You want to count the minimum number of cases the problem you're trying to solve has, right? In the search problem, I showed here that you need to consider at least n different cases. Okay. In sorting, you need to consider at least n factorial cases, right? In the assignment, you need to consider like some amount of cases, right? I don't know what it is. I mean, like, I know what it is, but I'm not gonna tell you. And then like you guys can figure it out. Then you just need to show that if you log that amount, that's the minimum amount of comparisons your algorithm needs to make. All right. So that's how you should be roughly like solving it. Okay. So with that, we're going to end this topic here, and I'm going to move on to the next one, and I'm going to show you guys the analysis for the full analysis for radix sort, because I think it's interesting and it has like some value in and of itself. All right. So one thing to note is that for most of the sorting algorithms that you would have learned before counting sort and radix sort, right? Like they all run in n log n time, and I've already talked about this, saying that for example, quick sort, merge sort, that sort of thing, the reason why they work in this running time, and you know, like when we say this running time, right, you have to remember this is we're sort of pretending that you can compare numbers for free. Like you can compare numbers in O1 time, you can shift your numbers in O1 time, that sort of thing, right? So in other words, when you do comparisons, you're actually accessing the bits. But you know, like when we're under the comparison model, we kind of say, screw it. You know, we'll pretend that you can do it efficiently, and we don't really care about that, right? So quicksort and merge sort kind of fall under that model of computation, and we see that they run in n log n time. And you know, like again, like I mentioned, if we only restrict ourselves to comparisons the way that merge sort and quicksort does, you might ask yourself, can we do better? And the answer is no, right? The solution was already shown in the lecture, so you can go back to it and revise it now if you're more comfortable with the proof idea, okay? And instead, what some people manage to show is that if, let's say, assuming that your values, let's say like of the input have bounded value, like are bounded, right? We can do better, right? So I'll explain what this means in a bit. Okay, but the point is that like usually when you run quicksort or merge sort, you don't really care about the input, you only care about the comparisons, right? So when I say you don't care about the input, right, what I mean is that the inputs can be of any value, the algorithm should still work. Okay. On the other hand, if I assume that my values of my input are going to be bounded by some range, right? So in other words, like every element of the array that I'm going to sort, let's say it's not too large, right? I can do better. And when I do better, I mean like we're going to try to target like O(n) time. Okay. So at this point, you know, like the first thing that you should think about, you know, wow, O(n) time is faster than O(n) log n, right? So what this means is that the algorithm that I'm going to be using shouldn't only use comparisons. Like it might use comparisons, but the point is that there has to be something more to this algorithm. It can't just use comparisons to solve it, to solve this sorting problem, right? Because if you only use comparisons, we fall back to the n log n bound. All right. So I'm gonna actually show you guys radix sort, like I mentioned, but let me first start with counting sort, because we're actually going to need counting sort here. Okay, so for counting sort, right? Let's assume, and let me make this general, right? Let's like assume each element of the array needs b bits to be represented. Okay, so in other words, right, like the input comes in as like, let's say A1, A2, all the way to AN, right? And I'm saying that each of these need be like in the worst case, or like let's just say like, you know, like to represent all of these, all of them need b bits. All right. So my first question to you guys is, right, how many, like, what do you think is the largest possible value that I should be expecting in the array, like in this, like amongst all the elements, if I need b bits to represent it? B to the power of n, that's not quite right. -1, not quite right. No, I mean, like if you're off by 1, I'm okay with that, because like, you know, we're in CS, like being off by 1 is our tradescraft. And B, okay, wait, so as in like each of these are different values. Each of these are different values. So this is like one value. Oh, hold on. Why is it not swapping to pen? What's going on? Give me pen. No, I'm saying like this is one value. So like this is element 1, this is element 2, this is element 3, this is element 4, this is element 5. Yeah, okay. Someone privately messaged me. Yeah, it's 2 to the power of b, right? So if I need b bits here, right, this value here has like in the largest possible value they can get out of it is to the power of b. Does it make sense? I mean, if you think about it, if I have 3 bits, right, that's like 8 possible value. Like you can go from 0 to 7, right? If I have 4 bits, like my values can go from 0 to 15. So I mean, you know, like the largest possible value is technically 2 to the power b minus 1, but you know, the point is it's roughly 2 to the power b. That's what I care about. Does this sit well with you guys? Like, is this okay? Because we're really going to use this. It's really important. So I need to know that you guys are like okay with this. Because if you're confused, you need to let me know. If not, I'm going to assume everything's okay and move on. Okay, no one's saying anything, so I'm guessing it's okay. All right, so element 1 has a value at most b 2 to the power of b. Element 2 has a value that's at most to the power of b, that sort of thing. Okay, so let's say that I made this assumption about my input. Let's say I made this assumption about my input, and I want to run counting sort, right? And the way that counting sort works is that I'm going to make 2 arrays, right? So the first array is going to be, let's say, something called the counting array. And the way the counting array works is that what we want to do is that for every possible value, right, we store a count of the items of that value, right? So in other words, this has to range from 0 to what? What's the what's the size of the array here? N. Not exactly. 2 to the power b minus 1. That's right. Right? Because if for example, like this index right here would say how many values, like how many elements here are of value 0, and how many elements here are of value 1, like how many elements here are of value 1, how many elements here are of value 2, so on and so forth, right? So in other words, like this, like the counting array sort of says like, okay, like for every possible value that could have appeared in the input, I'm going to count how many elements have that value, right? Since the largest possible value you have is 2 to the power b minus 1, the size of the array has to be 2 to the power b minus 1. Actually 2 to the power b, because like you start at 0. So like, I mean, this should be 2 to the power b minus 1, but the point is that the length of the array here has to be 2 to the power b minus 2 to the power b, right? Okay. Now that's the counting array. You still need the output array, right? So the output array is basically where you're going to chuck all the items in, towards the end. So that's the output array. Now this array is of size on. I mean, like it's actually of size n, but yeah. Okay, so the general idea with like using the counting array and the array n for counting sort is that you simply iterate through the input. Every time you see something of a certain value, you plus 1 to the index. Like for example, if this guy had a value 5, you go to the 5th, like go to 5 in this array, and then you just plus 1 to it, that sort of thing, right? If this is 5 again, oh, okay, then this becomes from like 0 to like 2. If you see another 5, if you somewhere down the road you see another 5, this becomes 3, so on and so forth, right? So you maintain a count of like all the values in this array. Okay, now there's a way to make it stable, which is the version that we want, because we want to use the stable version for radix sort. But I don't really want to go through the like all the details. It's slightly confusing. What I highly suggest you do is look it up, and they'll explain it to you guys. All right, but the point is that you kind of need to like do this reverse idea where after you're done with all the counts, right? So after you've iterated through the array, you need to actually iterate backwards from the counting array. And then you need to figure out like, I mean, you need to do like some sum first. So you need to do like a prefix sum. So like, in other words, you have to like take this value here and add it here, then take this value here and add it here, take this value here and add it here, that sort of thing. Then you need to iterate backwards on this. And then you'll be able to access the original array and like chuck the items in the correct manner. Now, of course, counting sort to you might sound, or that might sound complicated. You might say, oh, we already know the counts, right? So why do we even need the input? Why can't we just like output like as many iterations, like as many instances of the value that we see from the counting array? The answer is, I need the stable version. And the stable version kind of needs to move the input over. So again, the details are kind of complicated, but I don't want to say that to scare you guys. My point is that I don't have time to cover it. So you guys should really look it up, right? And try to figure out what's going on. the point is, again, all that work is to make it stable. So that's what you should bear in mind. If you can like remember that when you're reading the algorithm online, things should really make sense. All right. So the question next obviously is, what's the complexity? That's what we care about, right? So we need to iterate through two arrays. Well, actually three if you count the input, right? The point is that iterating through the input and the output arrays take O n time, right? But the size of my counting array is 2 to the power of b. Okay, so if I want this to be O n time, okay, b has to be at most log n. Okay, and bear in mind here, I cannot even say the following statement. I cannot say b has to be theta log n. Like, this statement is wrong, right? Because this statement says that b could be something like, let's say, 20 log n, 20 log n, right? Which is bad for me, because if I plug that in here, right, this is that my time complexity will be 2 to the power of 20 log n, which is the same as n plus, I bring this down, this becomes n to the 20. Right? So counting sort, right, only works well when the number of bits you need to represent it is like, okay, I mean, I can do like plus some constant here, that's fine. The point is that counting sort only does well if the range of the values that you're trying to deal with, right, grow as n grows. So that statement sounds kind of funny. Let me try to illustrate what I mean. So what this means, right, is that if I have an array of, let's say, size 5, okay, the values that I see here should be like, at most, let's say, for example, right, from like 0 to 5. That's all the values that I can possibly see. Okay, if my array size grows, let's say, to like 20 or something, then the possible values that I can see in my input go from 0 to, let's say, 20, something like that. The point here is that as my input grows, right, my counting array should grow at the same speed, roughly. Right, so if my input gets longer, my counting array is allowed to get as long, like roughly as long as it. It can be like 2 times longer, that's fine. It can be 3 times longer, but it can't be like n squared longer. So that's the intuition behind counting sort. So if you have this nice assumption about your input, we get this nice algorithm that runs in the O n time. Okay, but this is kind of a strong assumption. It's kind of bad, because it's a strong assumption, right? Like what if we want to deal with much larger values, you know? So we want to improve on this, and to improve on this, right, what we want to think about is what happens if my values, let's say all my array elements, right, were not just, let's say, from 0 to n, but 0 to, for now, let's say like n cubed or something. Okay, so in general, when I say this, what I mean is that I don't really actually want n cubed. What I actually want is something like nc c constant. So what this means is that, like, if I can bound my values by some 0 to some polynomial of n, right, then I'll have a linear time algorithm. So this is what I want to strive for today. Okay, and this is kind of like the main course of like today's tutorial. So we, again, like, I've already spoiled this. We're going to actually use radix sort somehow, right? And I also spoiled the fact that we're going to use counting sort to sort of like, like, build radix sort. So the way that I'm going to talk about it is kind of like this. Let's lay out the input. Okay, so let's say let's lay them out on the rows. So input 1, input 2, so on and so forth until input n. Okay, and what I'm going to do is I'm going to lay out exactly the bits that I need to represent this. So let's say this is 0, 0, 0, 1, 1, 0. This is like 1, 1, 1, 0. This is like 1, 1, 1. Maybe like 1, 0, 1, 0, something like that. So lay out all the bits that are required to represent the values here. Okay, I'm grouping it in a funny manner, but you'll see why I'm doing that in a bit. Something like this, okay? Now, what I'm going to do is I'm going to sort of like split this up into columns. Okay, and the way that I'm going to split this up into columns is that I'm going to say that for every b bits, that is one column. So I look at the first b bits, I'll call it column 1. I look at the next b bits, I'll call it column 2, so on and so forth. right? And then like the last, there's going to be some last column here. Let's just call it C for now. Like C, I don't know, let's say CR for now. Or let's say CD. I think CD would be nicer. All right, and this will also be B bits. I mean, you know, like if it's not like a nice like division, you can always just pad it with like some zeros at the back. It's completely fine. Okay, like pretend that there are zeros at the back. It's completely fine. Now, what I want to do, the algorithm that I'm striving for works like this. Okay, so I'll tell you what the algorithm is, and we'll try to analyze it. Okay, so I'm going to run counting sort, right, on the input, but only based on these, the first column first. Okay, then I'll work my way out. So I'll do counting sort based on this. So what you should see after counting sort is that these items should sort of like be permuted, right? And the way that it works is that if I'm ignoring all of these values, if I'm ignoring all of the values on the other columns, right, it's only going to be sorted based on like the first column. And you can think of this as your first digit if you want. I think that helps. So this is like the first digit that we're going to be sorting for, right? Then we're going to move up the column. We're going to do counting sort based on the second column, right? So on and so forth. So we're going to iterate through this. So like after the second column is done, we'll do it for the third column, then the fourth column, then the fifth column, what have you, all the way to the last column. Each time running stable counting sort. Okay, so it should be kind of clear that this algorithm works properly because you're sorting based on the digits first, then the tenths, I mean the quote unquote tenths, then you know like the hundreds and so on and so forth, right? But right now I'm not doing it based on like base 10 or whatever, right? I'm just saying B for like some general B. Okay. So my question is, what's the runtime? Right? And I argue that the way that you should think about the runtime, is it should be just considered as the number of columns, right? This is the number of columns tells you how many times that you're running counting sort, right? Multiplied by the running time of counting sort, right? For each run. Runtime of counting sort. Okay, and because like all of them have like roughly the same B bits, you know, the runtime should be roughly the same. Okay, so let's do the number of columns first, right? Let's do the number of columns first. If my values, right, if all the values that came in here, right, were bounded from like they were at least value 0 and they were at most value n to the power of c, how many bits do I need to represent this? In other words, I'm asking how wide is this thing? How many bits do I need? The reason why I need this is because I want to find out how many columns there are, right? Because the number of columns is going to be the number of bits needed to represent every value divided by b, right? So how many bits do I need? C log n, exactly right, right? Because like the largest possible value is n to the power of c, all right? So log n to the power of n to the power of c is how many bits you need, base 2 of course, right? Which gives me c log n. All right, so good. I have the number of bits that I need to represent each value, okay? And I'm going to be using b bits per column, right? So the number of columns that I need, it's going to be you know, c log n divided by b. Okay. Now the runtime for counting sort. So the runtime for counting sort is going to be n plus, because I have n elements here, so the input and output array are of size n, right? And I need the range, right? And we've already established this. Since it's b bits, the largest possible value that you need to deal with is roughly to the power of b, right? So this is like the size of the counting array. So this is your runtime. Okay, so the observation that you need to make, right, which I think is valuable in algorithm and design analysis, is that this this thing here, if b goes up, right, this entire term goes down because this is in the denominator, right? But the issue is that if b goes up here, b here also goes. If b goes up here, b also goes up here. So this entire thing goes up, right? So okay, so we know that we kind of want to increase it, but we can't increase it too much. Okay, what about the other way around? So if b goes down here, okay, this entire thing goes down. So this entire thing goes down. That's good. But if b goes down here, this entire thing goes up, right? So for example, if let's say I set b to be a constant, like 5. Let's say we pick some magic number, 5, right? The runtime here is on, right? So the runtime here will be on because this will be some constant. But because this is like some constant, right? You have a log n here. So your runtime becomes n log n. So now b is too small, for example, right? So we kind of have a balancing act. We kind of want b to be like this sweet spot where it's not too big and not too small, right? So and I've already spoiled it. We want linear time. So if we want linear time, what should we strive for? So for linear time, this needs to be theta n, right? What we can try for is this to be theta n and this to be O1, right? The reason why I can tell you that this is the case and like not any other case is because there's already an n value in the term here. So you can't try to make this guy any smaller. Like if this guy became any smaller, this is still n, right? So negative? No, you can't do that, right? Because if you like, how can 2 to the power b be negative? If like you set b to be a negative value, then this is just a fraction, right? Like you need it to be like log of like some negative value, but that doesn't even make sense for bits, because that would be like that even no, it doesn't even make sense. But anyway, the point is that if I set b to be log n, for example, like exactly log n, this is what we want. This is good for us. Because if I set b to be log n, this thing resolves to n, right? And if I set b to be log n, this thing is log n here, right? So then this resolves to be c, which is a constant by my assumption, right? So my runtime is going to be O1 times n, which is just On. All right, so this is the full analysis for radix sort. Right, you can try plugging in other values, right? You'll see that like if b is any larger than log n, this guy is going to be slow. If c is any if b is any smaller than log n, then this guy is going to start becoming like larger. So b is really the sweet, like b equals log n is really the sweet spot. Okay, so what's the moral of the story here? The moral of the story here is that if you assume some bound on your input, right, sometimes you can get really good results. All right. So let's talk a bit about, I mean, I still have a little bit of time left. If anyone has questions, you can ask now and I can try to answer it. If not, I can try to quickly talk about some stupid way to speed up shortest path finding algorithms. I really need to find the name of that algorithm. Like when I get a hand on my friend, like I'll ask him, because I think he showed it to his class in 2040 before. So I'm pretty sure it exists. I just don't know what the name is. No questions? Okay, so let's talk a bit about shortest path finding. And I kind of want to use a similar idea to counting sort. Can I explain the C-log2 again? Which part? So the runtime. So do you know why? Like I don't know which part you want me to explain. Do you know why it's C-log base 2n? Like do you know how I got this value? Is that what you're trying to ask? How to get that? So remember my values are at least 0 and at most NC, right? So if I look at any element in the array, this is the smallest possible value, this is the largest possible value I can get, right? So how many bits do I need to represent a value of this big? I'm going to need log of that many bits, right? So this is just C log n, right? So like maybe you might be wondering why log, right? Like you can think of it in like the opposite way, which is that if I have this many bits, how many values can I represent, right? So if I have this many bits, right, I can represent 2 to that many values, then just pull this guy down, this becomes n to the c. All right, okay, cool, good. I'm actually out of time, so technically whatever I'm going to cover now is out of class, as in like it's out of like class syllabus. So like if you have to go, like it's completely fine to go, because I've covered the stuff that I needed to cover. So like whatever's important, I've already done it, right? Because it's 9:50, so like if you guys want to go, it's completely okay. And like whatever I'm covering now is completely optional. All right. So with that said, right? If you have to go, like don't worry, it's recorded. You can like pop by and watch the video some other time. Like just skip ahead to like the 50th minute or something. If not, like I'm just gonna continue because I'm already here. You're already here. Like some of you are already here, so like might as well. All right. But again, like I stress, okay, like it's not compulsory. You guys can go. I've covered like whatever I need to cover. I need to say this because like the last time that I actually mentioned in my 1-2-3-1 class, like, hey, okay, whatever I'm covering now is optional, but you guys can call it a day and go home. People complained about it on teaching feedback, saying something like, oh, you know, like you should really stop dragging your classes. And I'm like, yeah, but I said you could go home. You know, and the funny thing was they gave excuses like some of us have classes to go to, and I'm like, you have a class at 6 p.m. Like it's probably not in uni. Like because I know that like classes after 6 p.m. don't exist. Like it has to be after 6:30 because like uni says that you need to eat at 6 or something. But anyway, okay, let's ranting more algorithms. Let's go. So let's try to solve this other problem where I'm given a graph G. Of course, when I'm given a graph G, what you should always think of is I'm given a set of vertices and edges. All right. So if you want to solve shortest path and the edges are unweighted, this is plainly very, very boring. You could just use like if it's undirected, you should just use BFS. Like maybe if it's directed, what would you use? I'm not sure. Maybe if it's directed, you should still run Dijkstra. BFS also? Yeah, I guess BFS would work, right? It should work. I'm pretty sure. I'm pretty confident it should work. Yeah, you're right. You should just run BFS too. Cool. So we care about the weighted case. So let's say our graph is weighted. Okay. But like let's say like positively so. I don't want to deal with the negative edges case because like we already have like Bellman fault for that. So now if I tell you right that I give you a graph, it has V like it's positively weighted, okay. The first thing you should think of is Dijkstra. Okay. Because that's really like the canonical way to solve it. Okay. And like based on my experience with the previous two tutorials, no one remembers Dijkstra or no one understands Dijkstra well enough. So let me quickly give an explanation. Okay. And fun fact, okay, Dijkstra, if I recall correctly, is both a dynamic programming and a greedy algorithm. So you can sort of like try to prove it. You can try to prove it. Or you can try to prove the overlaps. You can try to see where the overlaps happen. You can try to prove that there's optimal substructure. You can prove that there's a greedy choice, right? So let me give you an overview of what Dijkstra's algorithm does. So like apparently I needed to give a lengthy one. I don't know why. As in, I'm not saying it's your fault that you guys don't remember Dijkstra. I'm a bit more worried about the guy who was teaching Dijkstra during 2040 because I feel like it's a very important algorithm. And if you guys walked out of 2040 not knowing Dijkstra, I feel like that's partly the facilitator's fault. So okay, maybe I shouldn't say that. But as in I'm very concerned. All right. So since this is extra class, let me just cover Dijkstra. Okay. So you have some source node, right? And let's say you have like all these like other nodes that you want to find the shortest distances to, right? So you have all these weighted edges that like could be directed. Like maybe it goes in both directions. Who knows? Who cares? The point is that it's like we don't assume it goes in both directions always, right? And even if it goes in both directions, the weight in one direction could be different than the weight in the other direction, right? So maybe something like this, and they all have like weights, right? Like whatever weights. Okay. So what Dijkstra sort of says, right, is that like you want to build a frontier, a quote unquote frontier. Okay. So if you play Dota, right, like or like League of Legends, for example, or if you've played like Heroes of New Earth like I used to and then moved to Dota, right? One term you'd be very familiar with is fog of war. You can try to think of like Bellman Fort as like building up fog of war. Okay. So when I say fog of war, what I mean is that like basically when you start at the source, right? You sort of have you sort of like think that you don't know what the distances are to everything. So your view of every other location right now is that it's of distance infinity, because you don't have a good estimate of like how long it's going to take to reach it. Okay. So what you're going to do is that you're going to refer to the graph, look at the edges that you can take, right? In the case of the source, I can take like these two edges, right? Let me do that using blue. So these two edges right now are the edges that we can take. And then of course there's some weight to it, maybe like 1 and maybe like 15 or something. Okay. So what you want to do is that based on this view, right, you want to say that, okay, I have like these two locations that I can reach. I estimate that I can reach this location with distance 1. I estimate that I can reach this location with distance 15. That sort of thing. So right now, right, your fog of war like has decreased. So your view or your frontier of the map has kind of like, sort of like decreased to like this. So everything here you kind of like roughly understand. Okay. And you're going to of course have to visit like some of these edges, right? So the point is that mobile for instead of real-time strategy. Okay, yeah, you could also like have read alert or like command and conquer, but like I think I've like played those much. Okay, I don't know. Company of Heroes. Stop nitpicking. I'm trying to run a class. Okay. The point is that like what you want to do is that when you're on this edge, right, this frontier, this light blue line here, this is where you want to start pushing things out, right? So what the algorithm should do is that it should go to the nearest possible place where this has happened and start expanding it outwards based on the edges, right? So maybe you can push out in this way, push out in this way, that sort of thing, right? Okay. So the greedy choice that Dijkstra's algorithm makes is that when you ask which part of the frontier would you like to visit, your answer is going to be, oh, please, I'm going to visit like the, okay, actually like I guess this shouldn't be part of the frontier. The point is that to expand your frontier, right, you should always be picking the closest vertex to the source, right? So after you, okay, I shouldn't say the closest to the source, I should say the closest to the frontier. So every time you want to expand the frontier, right, what you want to do is that you want to say, okay, the closest node to the frontier, let me pick it, right? Yeah, closest node. So the point is that, okay, you want to argue that like the closest to the frontier is kind of like the closest to the source at that point in time, that sort of thing, blah, blah, blah. It's kind of like similar and stuff. So that's a greedy choice that you make. Go home and prove it. It's very good exercise, like really good exercise. It's a really good exercise. So this is kind of how Dijkstra works, right? And this is the idea, it's not the implementation, right? So like the original version of Dijkstra, I think, if I'm not mistaken, runs in v squared time because he actually did a very slow thing. So what he did was, oh, I have an array, okay, and this array is going to, like, one array keeps the actual distances, one array keeps like the distance estimates, right? So the distance estimates are the ones that like fit in infinity and like the other possible values, right? And then like the true distances are the distances that you hit at that point in time, something like that. Or maybe you only have one array, I'm not even sure anymore. Okay, but the point is that what he said was like, okay, we're going to pick the item with the lowest distance estimate, right? That should be where we expand our frontier. So that's the node that's the node that we're going to visit. Okay, so we go to that node, like we iterate through this distance estimate array, pick out like the node with the smallest distance estimate at that point in time. Okay, look at all the edges and use that to update all the other distance estimates as required, right? Then throw this guy out of the distance estimate, chuck him into the distance array. This is kind of roughly the idea, right? So you have to visit every vertex once. Every time you do it, right, you need to like update the distance array. Updating the distance array takes like degree of the node time, right? That's not so important. The point is that every time you want to pick out a vertex, right? Okay, you need to iterate through the distance array, distance estimate array, which takes like OV time or something, right? You need to do this like V times. So that's like V squared or something. It's horribly inefficient. Okay, but back then when he published the paper, that's what he went for. If I'm not mistaken, yeah, this is what I was told by a professor. He was like, "Did you know Dijkstra actually wasn't efficient?" Like when he wrote his paper. Yeah, cool fact. So then eventually people realize that, hey, like this distance estimate thing, let's not use an array. This is since v squared is equals to e. Well, what if e was smaller than v squared? What if e was less? What if e was v to the 1.5? What if e was v log v? You can be faster, right? You can do better, right? Like saying that e is v squared is only when you're considering complete graphs, which is fine. If you only care about complete graphs, great. But if you don't care about complete graphs, worst case analysis. This is not. I mean, this is like the worst. This is like the worst of the worst case, right? Like it's not even the worst case. It's like, assume worst case and then assume even worse than that. Like, assume like the worst of like the worst. Like if this was like worst case analysis, right? Like this is like what I mean by worst case, and like this is what you mean by worst case, right? No, I want something better. I want this, right? So where was I? Stop trolling. Where was I? Okay, so instead of using a distance estimate, what he said, what they realized was, okay, let's use a priority queue. Because a priority queue does a few things for me. It does two things for me that I want. I want to do decrease key. Okay, decrease key, and I want to do extract min. This is precisely what I need from the distance estimate data structure, right? And it turns out that when you use a priority queue, like when you use a min heap or something, right? You can do both these operations in log v time or log e. I don't really remember. It doesn't really matter. Okay. And if you try to swap it out for a Fibonacci heap, which is something that you will learn after you do an amortized analysis, or I can teach it to you guys for fun next time. Extract min, I think, takes amortized O1 time. Decrease key still takes log v time. Okay, so the point is that there are nice data structures that sort of support these two operations. You can plug them into Dijkstra's algorithm and you'll make them run fast. Okay. So what's the point of me talking about this today, right? It's not for 2040. We're going to use the counting, like we're going to use a similar technique to counting sort to build a slightly faster algorithm. Okay. In other words, what I'm going to say is that let's try bounding our edges. Let's try bounding our edge weights. Okay, so again, they're positively weighted, so no such thing as a negative cycle, definitely not possible. But I want one more assumption. I'm going to assume that my edge weights are bounded by like some value r. Is this dialed? Oh, is that the name of the algorithm? I've been looking for it for like days now. Is that the name of the algorithm? Okay. Anyway, let me finish this. Let me finish this. So when I say bounded by r, right? Think of it in like the usual way. So like for example, let's say like when I say r, I mean like 2e, or maybe like for example 2 log e, something like that. So what this means is that as my graph size increases, right? Okay, my edge weights can increase as well. But my point is that the edge weights can't shoot up too fast. Okay, so for example, for my edge weights to increase by a single amount, right? My edges first need to double, that sort of thing. This is what you should intuitively think of it as. Okay. So if you run Dijkstra using this, right? Dijkstra doesn't care about the edge weight bound. So what's going to happen is the Dijkstra is still going to run at the same time. So in other words, it's still going to run in E log V. Slow. Not good at all. Okay. So my point here is that the observation you should make is that priority queues are a comparison-based data structure, right? Much like how quicksort and merge sort are comparison-based algorithms. Okay, binary search trees, or like Fibonacci heaps, or like AVL trees or red-black trees are all comparison-based data structures. Okay, so we don't want to use any of that. Okay, or like we can use them, sure, but you know we need something more. We need something much better than that. Okay, so what I'm going to do is that I'm going to go back to Dijkstra's original idea, okay, somewhat, okay, but in the sense that I'm going to be using an array. Okay, so we're going to throw away heaps or any intelligent trees or any other special data structure, and we're just going to go back to using an array. Okay, but this array is not going to be like used in the same way that he did, right? What I'm going to do is that this array is going to again store all the possible distances that you will ever see. Okay, so if let's say, right, my bound on my edge weight is, let's say, bounded by r. So this is the largest possible edge weight you'll ever see, like the largest possible weight you'll ever see on an edge. Okay, and I want to store all possible distances that I will ever see on this graph, right? What should the length of this array be? Okay, asking what's the length of this array is asking what's the largest possible distance some node can be from the source, right? So if I have this bound, what's the longest distance I can get? Opening this question to the floor. VR? That's right. It's VR, right? VR sounds like virtual reality. It's VR. I mean, like it's V minus 1R, but like, well, who cares? Let's just call it VR. The reason why the largest possible distance you'll see is VR is because in the worst case, right, if all my edges are positively weighted, right, you only take at most V minus 1 edges to your destination, right? And each edge, let's say in the worst case, has value R, right? So the largest possible distance that you'll ever see is like V minus 1R. Screw it, let's just put it as VR, right? Probably wouldn't make a difference. So the size of my array is going to be OVR. Okay, and you'll want to sort of like run a similar version of Dijkstra in a very similar way, right? So again, you start from the source, right? And you want to grow your frontier, right? And remember how the priority queue sort of like tries to maintain this, right? So it sort of says, okay, I'm going to estimate everyone's distances. I'm going to keep track of like how close they are to my source, right? And then at every iteration, when it's time to look at a new vertex, I'm going to pick it out. I'm going to pick the minimum out of this priority queue, and I'm gonna look at all its edges, and I'm going to start like updating my estimates, right? I can do the same thing here, roughly. Okay, so the idea is going to be that what I'll do is that I'm going to start at this point, which should start at distance 0, which should only have the source, look at all its edges, and consider all the neighbors that it points to, right? And there's going to be like some edge weights here, right? So using all these edge weights, I'm going to try to chuck, right, like all my neighbors. So let's say this neighbor 1, this neighbor 2, this neighbor 3, this neighbor 4, right? So if let's say neighbor 1 is now of distance 5 away from the source, right? Okay, I go to like the 5th element, the 5th index of the array, and then maybe start a linked list and you know, like contain like N1, right? Then let's say, for example, N2 has distance 6. Okay, fine. I go to index 6. I chuck it in a linked list, and like I store N2 here, right? And if let's say neighbor 3 also has edge weight 5, so let's say these two have edge weight 5, I go here and I store like and 5 here, like sorry, n3 here, right? Because they both have like distance 5 away from the source. Okay, do this for all the neighbors. Once you're done, right? Okay, you know that you've considered all vertices of distance 0. Now you should move forward, right? Now consider all nodes of distance 1. Do the same thing, right? So the first time so every time, let's say for example you're at distance 5, right? And n1, this is the first time that you've seen n1. Okay, what you should do is you should say, okay, it's the first time I'm seeing n1, the greedy choice applies, right? So I need to update the distance, right? So like for n1, we're going to say you are distance 5 away from the source, right? Then throw it away. Do I still need to relax the neighbors? Yeah, you can if you have to, right? But check this array to make sure that you're not adding unnecessary vertices, right? Do for this distance, like iterate down the linked list. Once you're done with that, okay, you know that you've considered all nodes of this distance. There can't be any more nodes of this, any new nodes of this distance or distance less than it, right? So any new node has to be on the right side of the array. So rinse and repeat the same process. Okay. So in the worst case, right, you have to go through all the vertices, and you have to, and each edge adds a new node into this array of linked lists I've made, right? So the runtime should just be v plus e. VR plus e, I think. Something like that. So this should be, is it VR plus e or VR times e? I think it's VR plus e. It should be VR plus e. If not, this algorithm is not that interesting. So this should be our runtime. Okay, so in other words, right, if let's say R was constant, okay, you have a v plus e time algorithm for shortest path finding. Okay, I mean, okay, if R was constant, there are actually other algorithms that solve this problem, but it's, you know, it doesn't show what I'm trying to show you today. If let's say R is very small, let's say like log v, right? Then your algorithm runs in v log v plus e time, right? If let's say R was, I don't know, like log to the 1000 v, right? Then you have an algorithm that runs in v times log to the 1000 v plus e time, right? So the sensitivity of your algorithm depends on the bound on your weights, which I think is pretty cool. So, you know, again, if you remove the comparison based assumption and you as the comparison based like restraint, and you have some constraint on your input, right? Turns out you could possibly do quite well. So that's the moral of the story here. Sometimes it just works out that way. All right. So this is all I have for you guys today. Yeah. See you guys the week after, because next week is recess week. Have a good recess week, I guess. I'll stick around here just in case you guys have any questions for the next, like, let's say 5 minutes. But if not, the class is really over, so you guys can go. No worries. No worries. I just realized I've not had my coffee yet. No worries. I added like 2 sugar today, so I wonder how sweet it's gonna be. It's just theta max possible distance plus e. I think so, yes. So the way you do the analysis is that you realize that you have to at least iterate through the distance array. That's VR time, right? So I mean, okay, you can think of intuitively plus, right? It's kind of like a min operation if you think about it. Because if you're using theta, right, and one of them was clearly larger than the other, then you're like going to be theta of that one. That's how, like, theta with a plus on 2 terms is kind of like a max operation intuitively. I mean, this is not important. Like, you can just intuitively think of it that way. Okay, so you know that even if there aren't many edges, right? Like, for example, let's say the graph isn't even connected, right? You need to at least iterate through this this distance array. So that's going to be max possible distance. So that's VR time, right? The next question is, you possibly have duplicate nodes, right? Because like with the priority queue, you sort of just run this decrease key thing, but we can't do that here. At least I don't think we can do it here. There might be a way to do it here. Oh, there is a way to do it here, right? So you have a third array. That array sort of like points to the node on the linked list or something. And you also store, okay, so you store the pointer to that node, and you also store the distance that it's at, right? Then what you can do is, if you find a better distance, just delete it from this linked list and move it to the front. Ah, yeah, okay, so Do you even need E time? I think you, okay, at the very least, you need E time because in the worst case, you need to process all the edges, right? So like for every node, you have to go through like all its degrees. So the sum of the degrees is, as we know, 2e, right? So actually not 2e, right? It's undirected, so it should just be e. I mean, we're summing all the out degrees, right? So for every node, you need to process its degree exactly once, right? And we know that we need to iterate through the distance array. So this should just be max possible this plus e. Yeah, I think that sounds about right. So this is the running time, right? So for small ranges of r, right, like not even constant, it can be like a bit larger than a constant. You have good algorithms. Like I mean, you have a quote unquote good algorithm, right? I think I think that there is like a different way to accomplish this. So one way to do it is to like duplicate, like for every edge weight, you put in as many nodes as there are between the two vertices that contain the edge. But I forgot how efficient this is because you do increase the number of edges as well. So I think what happens is that if you try to do the duplication idea, this guy should slow down. So you might get like does it increase that much? I don't remember. Hey, the rest of you can go. I'm just like here in case anyone has questions. So if no one has questions, I'm gonna leave in like a minute or so. It's been a minute. I'm gonna leave now. Let me stop the screen share. All right. Well, have a good recess week. Bye bye.